The person who invented the relay was truly a genius. Let's see how it works. As shown, this is a simple circuit powered by a small battery. When an obstacle appears in front of the sensor, the LED in the circuit lights up. This setup is useful in many situations, like sensor lights. But if we want to do more than just light an LED when there's an obstacle, this circuit isn't enough. For example, when goods appear on a conveyor belt, we may want this circuit to start the belt. That's easy, just remove the LED and connect its wire to the motor input instead. Obviously, this is wrong. The sensor detects the goods and sends current to the motor. But the motor doesn't react at all. Why? Because the small batteries don't supply enough current to drive the motor. So what now? Simple, since the current is too small, we could remove the batteries and use a 220 volts power source. This voltage can easily run the motor, but clearly, this is also wrong. Because once connected like this, the control parts would burn out immediately. That's because these small parts have very low voltage limits. Even if they could handle the high voltage, the control circuit uses DC, but we're supplying AC. Unless we add extra parts like a rectifier, it still won't work. So what's the solution? Okay, it's time for today's main star. The relay, its function solves all these problems easily. The signal that once lit the LED will now switch the relay on or off. The 220 volts supply connects to the motor, so its power is now controlled too. Let's see how it works. There are many relay types, but today we focus on the common electromagnetic relay. Its structure is simple: an electromagnet, a movable armature, and contacts. The electromagnet is familiar, it's wired into the control circuit. When current flows through it, it creates a magnetic field. We learned this in school. Ampere's law says current through a wire generates a surrounding magnetic field. Based on this, we can make the conductor into a coil. This way, each loop's magnetic field stacks up, boosting the overall strength. If that's still not enough, we can insert an iron core inside the coil to further concentrate the magnetic field, making it stronger. Next is the movable armature, which is supported by insulating material, but has a conductive terminal near the top of the electromagnet. Take iron for example, it's magnetic and always attracted by nearby fields. So with the lever shape, the armature moves with the magnet to press or release the contact. Finally, the contacts, they link to a second circuit. In this state, the contacts are open, so the circuit is off. Back to our scenario, as shown, once current reaches the electromagnet, it generates a magnetic field. Key point: the armature's top terminal is pulled by the field and moves. Then its lower end acts as a lever to push the contact until the two meet. This closes the second circuit, the motor runs, and the conveyor starts moving. Simple, right? But we're not done yet. This relay is called a normally open switch. So is there a normally closed one? Bingo, yes! Its principle is simple. When the electromagnet is off, the circuit stays closed. When powered, the armature pushes the contact away to break the circuit. How do we choose between them? A simple example: the upper is normally closed, the lower is normally open. If we want a lamp to stay on 20 hours and off for 4, the better choice is the normally closed type. We only energize the relay for 4 hours. The normally open one would need 20 hours of power. Obviously, the latter uses much more energy. Another way to classify these is single pole, single throw. Pole means how many circuits a switch controls, throw means how many contacts it has. Now let's look at SPDT single pole, double throw. Based on that, we just add a contact. It's like combining normally open and normally closed. Each time the magnet switches, it breaks one contact and connects another, which is very useful. By adding another set of contacts, it becomes a DPT double pole, double throw. That means two identical relays are switched together. Here's an example. Use a DPT in our conveyor case to control motor direction. If the motor uses DC, its spin direction depends on wire polarity. So we wire each motor terminal to two relay contacts, one to normally closed, one to normally open. Each time the relay switches, the current direction reverses, changing motor rotation. Note, in this setup, we can't turn the motor off directly. To do that, add a switch to cut power to the motor. Lastly, some downsides of these relays. First, at high voltages, the contacts can ionize air and cause an arc. This raises temperature and can badly damage the circuit. Second, the contacts are springy, so they don't touch instantly, they bounce a few times before settling. This is called relay bounce. While bounce barely affects a motor, it can interfere with other circuits. These flaws are easy to fix. Use a solid-state relay with no moving parts or add an RC circuit to dampen bounce.